We have three goals in this video lecture. We want to understand graphs of exponential functions involving a base of e, so like the parent function being e raised to the x power. We want to use graphs to solve equations involving exponential functions, and we want to create functions where we want a certain amount of growth over a certain this sentence is a disaster. A certain period of time, which is not necessarily over the course of a year. Okay. So we'll start by the graph of e to the x, and this is our nice exponential function with a base that is the exponential constant e that we covered today. So you kind of have different sections here. You have your y-intercept, which happens when e is to the 0 power. That happens at 0, 1. And then what happens in this green section is we're going to approach a horizontal asymptote because we're plugging in negative x values, right? Over here we have negative x values. Okay, and when we raise a base to a negative exponent, then the way to rewrite that is with the base now in the denominator, and this number is just going to keep getting smaller and smaller and smaller. As this negative number becomes bigger, it's going to cause the denominator to become bigger, which is going to cause our overall output to approach 0. Now over here, we're plugging in positive x values, and those outputs are going to become quite large quite quickly. Here's a couple of examples. If I plug in x equals 4, my output's 54.6. If I plug in x equals 6, then I get 403.4. So you can see, even just by running by 2, we rose by about 350. So you can see in this blue section, we're just going to become steeper and steeper and steeper. So you should get this parent function down with the y-intercept at 0, 1. All right, if we multiply our inputs by a negative value, if we flip the sign of the inputs, that's going to cause us to flip horizontally. So we still have our y-intercept at 0, 1, but now the steeper portion is on the left and the horizontal asymptote is on the right. We have just flipped horizontally, so you should make sure that you get this transformation copied down. Okay, if we multiply with a coefficient, okay, in this case coefficient of 5, we can see that this is the red graph, which is not only it's steeper, right? It's 5 times steeper at every single x value compared to e to the x because we multiplied the outputs by 5. Okay, the y-intercept is now at 5 instead of 1 because if we do 5 times e raised to the 0 power, we're going to get 5 times 1, which is 5. So we have a y-intercept at 0, 5. Okay. So yes, we have our new y-intercept, and we also can see that this red graph is steeper than the blue graph at every single point. Okay. All right. What if we multiply with a coefficient that is negative? Well, that's going to flip the graph vertically, so let's not lose track of the x-axis here. This is our x-axis. This is our x-axis. Okay, so we notice that this has been flipped down, so it's now below the x-axis, right? Still getting steeper over here, still approaching the horizontal asymptote over here, but now we're exponentially decreasing, right? We're decreasing at an exponential rate. Okay. All right, so if we add 10 to our outputs, that's just going to shift it vertically. Adding 10 just shifts the graph up vertically, okay? So same steepness, just in a different vertical position. So for example, the derivative at x equals 1 would be exactly the same. All that's happened is that this graph has just been shifted up. Okay, so that's our vertical shift. All transformations that you're familiar with, that you've done with other types of functions, but now we're just applying them to exponential functions. So now let's look at these 4 examples and think ahead, what is going to happen to each of these graphs? Here's our parent function, right? So e to the x would be called like our parent exponential function. So then what's going to happen if we do 5 versus 0.5 versus negative 0.5? Give that a thought. Parent function, again, we've already talked about how e to the 5 is going to be steeper, right? Well, what if we take this 5 and we make it a number smaller than 1, like 0.5? Well, now that makes this graph less steep. You can see the exponential increase is more gradual compared to the parent function. And then this also has a gradual decrease compared to an increase, and it's a decrease because we have done negative 0.5 instead of 0.5. So these are 4 good comparison examples for you to have in your notes to reference. Okay, so now we're going to talk about our our general exponential function, which we just call poked informally, poked, because we have our p naught, which is our starting amount, e is our exponential base that we have been covering, and then k we're just going to call it like a growth or a shrinking constant, right? If it's positive, it's a growth constant. If it's negative, it'd be like a shrinking constant. And we're going to explore this more next semester, what's actually going on with k. But we can see in an example, let's say we want a town population of 2,000 to grow exponentially with a growth constant k of 0.02, then what will be our population after 5 years? So to set this up, we're just going to do 2,000, our p naught, right? Maybe I can label this up here. This is p naught, right? And then this is k. So we do 200 times e to the 0.02, and then 5 is going to be our t value, right? So 0.02 times 5, and that gives us 2,210 people about, right? So that's our estimated population after 5 years. Okay, now let's do a decay problem. So a car is brought brand new off the lot for $100,000. Okay, so that's P naught. It's our initial cost. Okay, it immediately starts depreciating with a decay constant of negative 0.015. How much is the car worth after T years? After 4 years, so that's our T. Okay, we have our K is negative 0.015, negative because we're decreasing. So we plug it in, 100,000 times e raised to the negative 0.015 times 4 gives us an amount of 94,176. So we've lost about $6,000 of value on our car. So the remaining question is, how is K calculated? How can we figure out that K value? And that's something we'll cover. It says later in the unit, but that's actually going to be our next quarter in quarter 3. So let's say we have an exponential function like this, 200e to the 0.06t, and rather than plugging in t values, we actually want to know when we reach a certain output. So I can plug in an input and I'll get an output, but what if I want to know the output that goes with a certain input? So there's going to be an algebraic way to solve this that we'll cover next quarter, but we can actually do this quite easily graphically, and I'm going to show you how. My screenshot got cut off here, so I'm going to have to write in what I would have typed into Desmos. So in Desmos, we're going to type our function, and Desmos doesn't like t as a variable, so we're going to use x. So we're going to type in 200 times e raised to the 0.06x. That's in our first cell. And then the slide, this isn't a slider. What we're going to type in is we're going to type in y equals 250. And what that's going to do is it's going to give us this horizontal line that just shows us where the output 250 is. And then we just have to see where they intersect. So here's the graph, 200e to the 0.06 t. And then here's 250. And they intersect at t equals 3.719. So what that means is 200 times e to the 0.06 times 3.719 is going to be equal to 250. So after 3.719 units of time, whatever our units of time are, we're going to reach our value of 250. So that is a quick graphical method to solving any equation by just looking for that intersection point. All right, so then what if we have a function like this? We're going to stop talking about e for a second and just look at a different base function. So our base here is 3, right? So that tells us that we are tripling, right? Because we're multiplying by 3. Okay, that could also mean 200% growing by 200%. Growing by 200% to a total of 300%, right? So we're growing to 300% of what we started. But what's going on with this x over 4? That's what we really want to explore here. What is this doing? And obviously we have an initial amount of 10, right? Initial value of 10, okay? And we're tripling. But what's going on with this x over 4? Okay, that's what we want to explore here. So we can see that if we were to plug in x equals 4, then we would do 10 times 3 to the 1 power, which is just 10 times 3. Oh, so we've tripled. We've taken 10, we've multiplied it by 3, and we got 30. If we plug in x equals 8, we're going to do 10 times 3 to the 8 over 4, but 8 over 4 is just 2. So now we're doing 2 times 3 squared, which is 90. Oh, we've just tripled from 30 to 90. If we plug in 12, we're really going to be doing 12 divided by 4 up here. So we do 10 times 3 to the 12 over 4, which is 10 times 3 raised to the 3, which is 270. So we've tripled. Okay, we've tripled from 10 to 30 to 90 to 270. And how often is this happening? Well, it's happening 4, 8, 12. It's every 4 years, or every 4 units of time, we should say. So we're tripling every 4. What do you want it to be? It could be every 4 weeks, right? Maybe it's every 4 days. Maybe it's every 4 years. Okay? You get to, it depends on the situation, right? You get to decide. But what this is going to do is it's going to allow your amount to triple every 4 units of time by doing the variable divided by that 4. And we can see why that works here, because if we do 4 divided by 4, that's going to allow us to triple once. If we do 8 divided by 4, that's going to allow us to triple twice. If we do 12 divided by 4, that's going to allow us to triple 3 times, right? And so that means that after 12 units of time, we have now tripled 3 times. Okay, here's another example. We want to have an initial amount of 12 that increases by 50%, so to a total of 150%, or 1.5, every 5 units of time. So I do 12 times 1.5 raised to the x over 5. Okay, so now if I do f of 0, what that means is I'm doing 12 times 1.5 to the 0 over 5, which is just going to be 0, so that's just going to give me 12, right? What if I plug in 5? That's 12 times 1.5 to the 5 over 5, which is 12 times 1.5 to the 1, which means I'm just going to multiply by 1.5, which is going to give me 18. So I've now grown by 50% in 5 units of time. And then if I do 10, it's going to be 12 times 1.5 to the 10 over 5, which is 12 times 1.5 raised to the 2, which means I'm going to grow by 150% twice, right? I'm going to multiply by 150%, and then I'm going to multiply that by 150%, which means that I'm going to grow to 27, because 27 is 150% of 18, 18 is 150% of 12. Every time we grow 5 more in the x direction, 5 more units of time, we're then going to multiply that value by 1.5. Okay, so let's do another practice problem. Determine starting amount, okay? So starting amount is 100. Percentage, it's growing 2, okay? So growing to 175%. So it's growing by 75%, right? Okay. And then it's happening every 10 units of time, because we're doing that x divided by 10, okay? All right, so here's your closure, which covers some of the stuff we did synchronously in class today, and then some of what we covered in this video lecture today. And you will do this closure and then submit your work to Google Classroom.